Okay, so welcome everybody. So today we actually have Dr. Student Ichu. Ichu, have you finished your defense yet?
No, I just finished my proposal, not the
Okay. All right. So Ichu is a PhD student at School of Computing, University of Utah, and he works very closely with Vivek over natural language processing. So he's going to be our guest lecturer today to give us an introduction to natural language processing. And also, if we have time, we're going to talk about history of word embeddings. And next lecture, which is next week, I am going to go over some Python notebook, Jupyter notebook to go over some of those actually codings for natural language processing as well. So Ichu, do you want to introduce yourself and say a little bit more about your research?
Yeah, hi everyone. My name is Ichu Zhou. I'm a PhD student for University of Utah, and my research area is natural language processing and machine learning. And more specific, my research project is more so about word embeddings, how word embeddings are trained, and how the word embedding encode linguistic information. And basically, that's my first research area. So today I'm going to first thanks space invitation. Here I'm going to give a guest lecture about the introduction of natural language processing. Actually, I will break this talk into two parts. The first part is the introduction of natural language processing, and the second part is about a little history of word embeddings, because word embeddings are the very fundamental problem in NLP. It's very important, and I think it would be interesting to discuss some history of the development of the word embeddings, how we represent representations over, how we change the representations over the years, and how do we come to the model that we are using today. So before that, I will start with the introduction of natural language processing. Before talking about any details of the natural language, let's think about how do we communicate with computers. In our imagination, we are supposed to communicate with computers using our natural language, just like talking to a friend. But sadly, currently this only happens for sci-fi movies. So in reality, we actually have to use some input equipment to talk to the computers, like a keyboard and a mouse. And even with these actual equipment, we still need a programming language to let the computers understand the instructions. So this is a little frustrating, because what we really want is we can directly talk to a computer. So one of the ultimate goals of natural language processing is we want to get rid of all these input equipments and directly talk to a computers. I think it would be really cool if we can have a real C3PO working beside us. And in this talk, I will start with explaining what is NLP and what applications NLP can provide. Then I will talk about the challenges of the NLP are facing, and why can't we have a C3PO now, and what makes it difficult to build a C3PO. And then I will talk about some techniques of NLP, mostly as based on from machine learning field. And at last, I will talk about the future of natural language processing from my own perspective. Okay. Let's start with the definition of NLP. This definition comes from the Wikipedia. It says that natural language processing is a subfield of linguistics, computer science, and artificial intelligence. It mostly focuses on the interactions between computers and human language. In an NLP conference, you are expected to meet people from different backgrounds. I think that's a very exciting and interesting experience. NLP is trying to identify the structure and the meaning of words, sentence, text, and compositions. It wants to have a deep understanding of broad languages. Here, I have tree-style structures here. Computers will understand this sentence with the help of this actual information. For example, with these tree structures, computers can understand which words are the nouns, which words are the verbs. Giving a sentence and finding a tree structure like this one is one of the typical tasks of NLP. The previous example might be a little too specific, so let's see some real applications of NLP. And I think the most widely used NLP application is machine translation. Currently, I think the quality of machine translation is quite good, although sometimes the translation might still not grammatically correct, but it is understandable. And the one beautiful thing of current machine translation models is we do not need to design a model for each pair of languages. Instead, with the help of the machine learning models, we only need to design one model, and we can translate between any pairs, not any most of pairs of languages. Another widely used NLP applications is the visual assistants like the Siri and Alexa. Before you say anything, I know sometimes they are very stupid, but in other times, they can be very helpful. For example, they can help you access your photos. They can search answers from the internet for your quick questions. The techniques behind the visual assistants are all based on the progress of natural language processing. Another real application is the web search. Nowadays, the web search is no longer a simple strings match anymore. It's everything you type in a search box will be interpreted by a model, and the model will try to understand your questions and find the most portable answers for you. For example, here, Google knows the color of a banana, and Google also knows the capital of Utah. Okay, we have seen the definition of NLP and have seen some real applications of NLP. So let me talk about some of the challenges of NLP are facing and why it is difficult to have a real C3PO now, and what makes it difficult to build one. The first challenge here is the ambiguity of languages. And languages can be very ambiguity, and the ambiguity can happen in any form. For example, I have a news here. The title says that the tunnel record the land on sale. So how can we how should we interpret this sale? When we look at the definition or the meanings of sale from Wikipedia pages, there are so many things that are called sale. It can be an animal. It can be the musicians. It can even be a law, and even it's a U.S. force. So how do we interpret here? And I think at least some of these definitions can be a reasonable interpretation here. For example, I can say the tunnel record the land on sale because these cans are not properly secured, thus the tunnel inside go wrong. And another interpretation is tunnel record the land on sale because that batch of product is not authorized by the company. It used a wrong sale. And even another interpretation can be the tunnel record the land on sale because there was an accident caused by the animal sale. Although it's unlikely, but it's a possible explanation here. So there are so many different interpretations here, which makes the understanding of the language is difficult. And the ambiguous can have many different forms. Here, for example, the olive oil, it means oil made from olivers. And in the similar form, the baby oil, we understand that it means the oil made for babies. I don't think anyone will interpret as the baby oil made from babies. So that's for humans, as humans, it's quite easy for us to distinguish the difference, these ambiguities, but it's a disaster for computers. Another example is like the diamond ring. It means the ring with a diamond. And in the similar form, the gold ring, it means the ring is made of gold. And the nose ring, it means something completely different. It just means the ring is for the nose. So there are so many different ambiguities here. And here are more examples. I ate sushi with tuna. I ate sushi with chopsticks. I ate sushi with a friend. We have the similar form. We have similar forms of the sentence here, and we have three different ways. And these three different ways have completely different meanings. So the ambiguity can take any forms like lexical, syntactic, and semantic. That's the most most difficult for computers to understand the languages. The second challenge of language is its dynamic nature. Language are actually always evolving. It changes every day. We are creating new words every day, and it changes meanings every day. Here I have three examples. For the first one is a Googleization, and clearly this word is derived from the Google, the big tech company, which does not exist 20 years ago, and yet now we are creating new words for it. The second word is the word sad. It's commonly used in social media. We as humans, we can easily understand that this sad is equal to the word sad. It's just an emphasis of the emotions. However, as far as the computer considers, it's just two different lists of strings, and they have completely no connections. So that's one difficulty that how do we teach computers to make connections of these different forms of words. And the last example here is a low square. I think this example is a very good example of the creation of, shows the creation of the humans. We can create new words, and it can be easily understood by other people. Like the example here, the no square, it just means a big no. However, for computers, again, for computers, it's just a different list of strings. So it's quite difficult to use rules to describe these different variants of words, because people can change in any different directions. So it's quite difficult for computers to understand these things. And some of you might think that the language are changing in the speed of dozens of years, but actually the language is changing much faster than you think. For example, here is a table of the online chatting, the vocabulary for the online chatting. And I have to say that I do not know all of them, even though I was born after the creation of the internet. So more importantly, we are creating the operations every day, more and more. We are enlarge this vocabulary every day. And also the meaning of each operations are also changing. For example,
true. Sorry, there seems to be a technical issue. I will contact Ichu to see what is going on.
hello.
Hi, welcome back.
Sorry, my connection is not very stable. I think I lost connection for a few seconds.
Yeah,
Yeah,
it's fine.
So can you see my screen now?
Yes, probably the last page, because you kind of disconnected from the last page, not this page.
Okay.
Or
this page?
yeah, this one. Thanks.
Okay. I guess I have to restart with this page. Okay. So in the, I was saying that the meanings not only the language is dynamically changing, and we are not only adding more abbreviations to the vocabulary, but also the meaning of the existing abbreviations are also changing. The examples is the AROAR. It changes from nav out node to I have nothing else to say. So and this table also shows another. Oh, sorry. Yeah, this table shows another table of the cyberlingos from another domain, and I think these are quite difficult to understand if we are not in the community, in that community. So anyway, so what I'm trying to say is the language is evolving and it changes in different domains, in different regions of. So it's quite difficult to natural computers to catch up. Even it is difficult for humans to catch up all these changes. Except the dynamic nature and the ambiguity of languages, there are still so many other linguistic phenomena that prevent us to build a real C3PO. For example, the metaphor, it makes my blood boil, it's the apple of my eye, or the metonymy, that the for example, the White House said today, blah, blah, blah. And the idioms that I'm under the weather, I want to take a day, 1 day off. So if we try to interpret this phrase just literally from the meaning of each word, it does not make any sense. So in order to understand these phrases, we require the meanings more than the just the meaning of each word. We need some common sense of the word. Sometimes even we want some history knowledge to understand these different phrases. And that's a big difficulty for computers, because computer does not have any common sense of the word. It's just to know, it's just to read the list of sequence. Okay, I've talked about the challenges of the languages, why we can't have a C3PO. Now let's look at some techniques of NLP and to see what we have done in NLP, in the field of NLP. In the early stages, the NLP systems are usually based on rules because at that time, people were convinced that a bunch of rules are sufficient enough to describe the phenomena of languages. So at that time, a list of rule-based systems were developed, and it was deployed to help in the wild to help people like the chatbot and other applications. But after a few years, people start to realize that the rule-based systems only worked for a very small set of examples. And more importantly, it took several years to accumulate effort to create such a system, because it requires experts to write rules, to analyze some phenomena and write specific rules for each phenomena, and also need to make sure that the rules are not contradicting from each other. So even though these systems cannot generalize well, so what it means, the handcraft rules do not really reflect how language works in practice. So what can we do? At least rules are not the best ways to handle these language problems. So what can we do to address these natural language problems? Fortunately, with the development of machine learning, we have new tools to help us to address this natural language problem. The combination of NLP and the machine learning is they are a perfect match for each other, because in machine learning, it really requires a large amount of data to train the model. And in NLP, we have plenty of text. we are creating text every day. So the combination of these two are a very natural choice. Once we choose machine learning to handle the natural language problems, it's like opening a door to a new whole world. There are so much to explore, and there's so much new to master to handle these natural language problems. So let's start with the very basic problem of NLP. How do we present the meaning of each words? The word bunny and the word sunny, they are only one word later apart, but they are in the meaning they are very different. They have very different meanings. But bunny and rabbit, they are not even have a common letter, but they are very close in the meaning. So from the perspective of machine learning, how can we learn their meanings from the data? Generally, rules are not a dictionary, or rules are not a choice here. So the idea is very simple. Actually, it's a very old idea. Gerald first, it proposed this idea in 1957. Which says that you should know a word by the company it keeps. What it means is the meaning of a word is determined by the labeling words. This is actually, I think, intuitive, because when you mask one word in a sentence, it is still with high probability that you can guess the meaning of the masked word. Here is a simple example. I would like to eat of a cake. So which piece should I put in this blank? It seems easy. For humans, we know which piece should be put, but for computers, it might be a little confusing. So the idea is we can train a binary classifier from a large amount of data to make these decisions. And we can use the features of the context, meaning the words before the blank and the words after the blank as the features to feed into this binary classifier to make the decisions. And in the simplest case, we can use the indicators of the labeling words as the features. And in practice, we find that this simple setting works very well. It shows the power of the combination of data and data features and the learning algorithm. When we combine these three things together, we got the profit. This is a very good example showing the combinations, the fusion of the natural language knowledge and the machine learning models. The natural language knowledge tells us that the meaning of a word is determined by its context words. So using this prior knowledge, we design a model that take in the context words and make predictions for the current word. So let's go back to the original problem. How do we represent the meaning of each word? Here, in the last example, I use the indicators of the labeling words as the features. Actually, this is also a very old idea. We represent every word by a very high dimensional vector. In this vector, this vector is called one-hot representation. I will talk this more about in the second part of this talk. But now I just want to mention that this one-hot representation is a very high dimensional, a binary dimensional vector, and every dimension representing a specific word in the dictionary. For example, here, the room is the first dimension representing the room, the second dimension represents Paris, the third is for Italy, and the fourth for the France. So when we want to represent the word of Paris, everything else in this dictionary, in this vector is 0, except the second dimension, it will be set to 1. This is a very simple representation, and as you can imagine, there are many problems of these representations. The first one is, in order to cover all the words in the vocabulary, we have to set the dimensions of this vector equal to the size of the vocabulary. which can be quite large. It can be easily in millions. So it's not very efficient if you want to use these one-hot representations. And the second problem of this one-hot representation is it does not contain any semantic meanings. For example, we know that all these Rome, Paris, Italy, and France are the cities, but we cannot get this information just by looking at these one-hot representations. Basically, there are no big difference between the words. It's just different positions of non-zero values. So in order to overcome these problems, a newer idea is instead of representing each word with such a high dimensional vector, we can represent each word as a lower dense vectors, which is called word embeddings. It's actually a very hot topic recently because we have achieved a great progress on word embeddings. But today I will not talk about go into the details of the word embeddings. Here I will just talk about some beautiful properties of these word embeddings. Basically, word embeddings are just a product of machine learning models. Nowadays, it is usually a huge, very complex neural network. But the beautiful things of these word embeddings is the first one is it has a fixed size of fixed dimensions. It's usually in a few hundreds, sometimes in a few thousands. So it is considered as low dimension compared to the size of the vocabulary. And because of its fixed dimensions, it's relatively easy for us to handle these vectors. Another beautiful property is these word embeddings can capture semantic meanings. For example, some of you might have seen this equation in other place. King minus mine plus woman equals the queen. These operations are conducted on the vectors. So this equation are good evidence to show that these word vectors can really capture the semantic meanings. At least it captures the male-female relations. But if we look into the vector space more closely, we would find that it captures more. For example, it can capture the verb tense relations. It also can capture the country capital relations. It's a quite amazing things to me because originally in one-hot representations, they are just points, random points in the vector space. It does not mean anything, but now we have found some patterns in the vector space. I can say that this region means the concept of color. In other regions, means the concept of sports. So with the help of these high quality word embeddings, we actually achieve a great success on high level NLP tasks. The next techniques I want to mention is part of speech tagging. As the name suggested, this task tries to identify the part of a speech of all words in a sentence. For example, it will identify which word is a noun, which word is a verb, which word is an adjective. These labels can provide actual information to describe the structures of the given sentence, and this information are usually feed into high-level NLP models to help the computers understand the sentence. So one standard way solution to this part of speech tagging is a sequence model. Again, I want to go to the details of the sequence model because there are so many variants here, and it is still an ongoing research direction. But the basic idea is we should assign a probability to the entire sequence. And we also need an inference algorithm to search for a sequence that maximizes this probability. This part of speech task is another good examples, the combinations of the natural language knowledge and the machine learning models. Because these labels, part of these labels are created by linguistic, and the linguistic will annotate a data set. And then we will train a machine learning model on the annotated data and make predictions for the future sentence. So the labels are created by linguistic, and the model is powered by the machine learning. The next technique I want to mention is the information extraction. This is also a very useful technique, especially when we want to build a database about the entities and events from the text.
Hi,
Oh,
Yichu.
hi.
So there's a question
Okay.
from Garrett saying that what are the dimensions of these vectors considered as?
Okay, you are talking about word embeddings, right?
Yeah.
Yeah, usually in 2013, it's early stage for embeddings. It's usually a few hundreds, like 300. But nowadays, the most state-of-art word embeddings is about a few thousand, like 1024 dimensions. It's just a choice, but it's doesn't mean anything. It's just a choice when we design the models. Yeah. Okay, any other questions? Oh, I just see the question. Okay, I will just continue. Okay, one specific task of the information extraction is called named entity recognition. In this task, we want to identify all the named entities in the text and their types. For example, we are given a sentence says that Martin lives in Banana Bear and works at Bananas Inc. In this sentence, we could extract that the Martin is a person, and the Banana Bear is a location, and the Bananas Inc. is an organization. So with the help of the technique of information extraction, we can extract these entities from this sentence. And I think this is the most important information from this sentence. So we can feed this information for the next step of another NLP system. So it's quite useful because it can extract it can be very useful if we want to summarize a document. Right, we can extract all these entities. The last technique I want to mention is sentiment analysis. In this task, we want to predict whether the given text has a positive or negative polarities. This technique are usually used in the social media or some review websites. Here, I have 4 examples from the movie reviews. The first sentence, sometimes the sentiments are very easy to detect, but in other times, it's very difficult. For example, in the first sentence, it just says the movie was so awesome that I want to watch it again. Clearly, the word of awesome is a very positive emotion. So it's easy to detect that the sentence is a positive review. And the second sentence says the movie was terrible. This is also very easy because the word of terrible has a clearly negative polarity. And but if we look at the third sentence, the movie feels like they finished the filming before completing the script. There are no any positive or negative words in this sentence. But again, we as humans, we can understand this is a negative review, but it might be quite difficult for a computer to understand, to assign a label for this sentence. And more difficult examples is the last one. It says this movie was done and converted, but I like it anyway. So it's kind of express some mixed feelings. So it can be classified as positive, but it's also reasonable to classify it as negative. So it's quite difficult for to develop a good system to make the correct predictions. Okay, any questions about the techniques I have covered? Okay. I have covered a few techniques from NLP, and at last, I want to talk about some future directions of NLP from my own perspective. In recent years, I think the people are start to teach high-level semantics to the machine to the models. One of the typical tasks is called natural language inference. In this task, we are given two sentences, which called premise and hypothesis. For example, the premise here and the task is we need to predict the relations between these two sentences. For example, here the premise says before it moved to Chicago, aerospace manufacturer Boeing was the largest company in Seattle, and the hypothesis says that Boeing is a Chicago-based aerospace manufacturer. So we can say that the premise entails the hypothesis, and so the model is asked to predict one of the three labels here. So we consider this example as high-level semantic task because it not only requires the model to understand the sentence, but also requires the ability to reason about this sentence. To make the correct predictions, the model has to have some ability to reason about the relations of the two sentences. And this plot shows the development trend over the last few years of this natural language inference task. As we can see here, before 2018, we can only achieve like 72% accuracy. But as the January 2020, we can already achieve about 92% of accuracy. We have achieved a 20% improvement over the last 3 years. It's quite amazing, I think, in just considering it only takes us 3 years. So you might think that we already resolved the problem of reasoning. It seems models have the ability to reason about the language. But I have to say this is not true because this plot only focuses on one specific data set. And a deeper analysis have already shown that the models do not really have the ability to reason. Instead, it has the ability to memorize everything. When we apply the model to a different domain or different topic, the performance drops a lot. So which means the model only memorized everything, and it specifically memorize this data set, and it can such that it can achieve a very high performance. But in reality, it still does not know how to do the reasoning. The next future directions is question answering. This is a technique behind almost every virtual assistant. This is a technique behind the Siri and Alexa. At least one of the techniques. Okay, the task is we are given a passage, a segment, and we are given a question, and the computers are required to answer the question based on the passage segment. This task is considered to be a harder task than the natural language inference because it requires more reasoning, and it needs to find the answers in the given segment. And this plot shows a development trend in the last 3 years, similarly to the natural language inference. Only from this table, we might see that we have a big improvement on this task. Before 2017, we only achieved like 65 F1 score, but in 2020, we have already achieved almost 95%, 95 F1 score. It is a huge improvement, but similarly, I have to say that this improvement, most of them is because the models are try to memorize data set, and not the model have the ability to do the reasoning. So, but still, I think this is a good sign. It shows the promising futures of to teach the reasoning ability to the computers. Okay, I have talked about two high-level research directions in NLP, and now I want to talk about another research directions in lower level, which is repetitions. I have mentioned that the word repetition is a very important and fundamental problem in NLP, and we have the techniques that we can represent a word into a vector space, but these techniques can be actually extended to beyond the words. We can encode the meaning of a phrase into a vector space. What about sentence, document, or a network or knowledge? We have a huge knowledge base like Wikipedia. So can we incorporate everything into a unified semantic space such that it can benefit all other natural language tasks applications, because everything else have to use some repetitions of the word. And if we, I think this direction is also very interesting and exciting, because once we have some breakthrough in these directions, it can benefit all other applications. And it is even possible that can bring a real C3PO into life. Okay, are there any questions about these future directions? Okay, except the directions I mentioned, like the QA and the natural language inference and the word repetitions, actually there are more application directions in the future. For example, the mental health therapy. The systems can keep tracking the dialogues between a patient and the counselor, and it can try to track the mental health of the patient, or it can score the therapy, try to quantify the quality of the therapy. And another, I think another important direction is machine translation. Also, I know that the current machine translation model is good enough, but I think it still has space to improve. And myself as a non-English speaker, I still have to use machine translation from time to time. And yeah, I really hope that the machine translation can keep improve its performance. So another promising future direction is the medical diagnosis, because the systems can read the charts of for many patients, and they can help the doctor to make diagnosis. Because clearly there are some patterns in the symptoms and the disease. So it is natural to think that we can design a model to make diagnosis based on the descriptions of the symptoms, and all these symptoms are in the form of text. So that's why we have NLP models to attack this problem. So yeah, it's kind of exciting. So in the future, it is possible that we will be diagnosed by a computer. So there are many other future directions very promising and can really reshape our lives. So I have shown a few directions for the NLP, and we can really transform the method of communications between the computers and the humans. But again, we have still a long way to go, because there are still a lot of challenges ahead of us. I will talk about some challenges from the technical level. The first challenge is repetitions. So I have mentioned this several times that the repetition is a really important and fundamental problem in NLP. So what is a good repetition of language, and how can we get it? This is a really important direction, and I think this is going to be always going to be a hot topic in NLP. And the second challenge is the data. Although we have we have almost unlimited text data, but machine learning model requires is annotated data. But annotations requires expertise. It requires time, requires money, and it's very expensive to have real high quality annotated data. So how do we get around the need for annotated data? There is a field called unsupervised learning, which is trying to use annotated data to feed the machine learning models. And I think that's also going to be an interesting direction. The next change is the reasoning. As I have said earlier, that the current model seems to have the ability to do the reasoning, but in reality, it does not. It just memorize everything. So how do we force the model not to memorize? Instead, it should to learn the ability to do the reasoning. It's still a big problem in the future. And at last is the common knowledge. I also mentioned this before. In order to let the computers to understand the language, we need to inject, we first need to represent the common knowledge, and then we need to inject this common knowledge into the computers. So how do we inform the model of common knowledge is also a big issue. There are some attempts, but it's not very successful personally, I think. So it's still a big research direction in the future. So I have talked a lot about the different aspects of the natural language processing. So let's take one step back and look at the bigger picture. Overall, we want the programs to that have the ability to read, understand, and reason about the text, just like humans. So in sci-fi movies, we have seen a lot of robot figures like Mr. Dead. They can communicate with humans. But in reality, we cannot have them. But I want to say that we are in progress to build a real C3PO. There are a few lessons from this from the field of natural language. So first lesson is representation of the text really matters for building applications because computers see the world differently. Computers are good at numbers and we humans are good at symbols. So how do we represent symbols into a format that computers can understand is a really, really important task. And the second lesson here is we already know that the rule-based systems cannot generalize well. So here, this is why machine learning is a good tool, perfect tool for us to address the language problems. And the third lesson here is the domain knowledge still helps. We cannot say that we build a machine learning model and let it to solve the every problem in language. We need to combine it with our domain knowledge. The one example is in NLP, we know that the meaning of a word is decided by the content, by the neighboring words. So we needed to design some models that extract features from the context and make predictions for the current word. That's the combination of the domain knowledge and the machine learning. And then the last point is the good data helps train a better model. In the field of machine learning, the general principle is more data, better model. So how do we have? How can we have a high quality model? Yes, high quality annotated data is also a very important aspect of natural language processing. And this is the end of this first part of this lecture. So if you have any questions, please ask me anything. Yeah.
All right.
So okay. So if there's no any questions, I think we will go to the next slide. Okay. In this slide, I'm going to talk about the little history of word representations. Sometimes we call it word representation, sometimes we call it word embeddings. I think basically it's mean the same thing. I think this topic is interesting because yeah, it is interesting to know that how different word representation evolve over the times, and how do we come to the model that we are using today. And you can see that in every stage, the new ideas always comes from the previous ideas. It's some kind of very interesting. So here I divide the history of word representations into 5 different stages, and try to map these stages to the stages of human history. At first, we are in the prehistory. In this stage, we only use a simple dictionary lookup to represent each word. And then we will enter the Middle Age. We will use one-hot representations. I called this stage as Middle Age because although one-hot representation is very simple, but actually it is very useful in practice, and we have been using them using one-hot representation for many years. And then we will come into the enlightenment stage. In this stage, the concept of dense vectors were proposed, and but at that time, the word vectors only exist in the theory because at that time we do not have enough resources, and we do not have efficient algorithm to learn these word vectors. And the next stage is the industrial stage. As the name suggests, at that time we have enough resources and we have efficient algorithm. So there are so many models were proposed at that time that they can all generate high quality word embeddings. And the next stage is the modern age, is currently what we have now. It improves word embeddings further by make a distinguish between the type vector and the token vectors. I will talk about this later. And at last, I will give a brief summary about the different stages of the history of word representations. Okay, so let's start with the prehistory. In the prehistory, we simply use an integer to represent each word. We will assign an integer to each word in the dictionary. So for example, here, suppose we have a vocabulary only have 3 words, and I'm Groot. So I'm adding one more extra word to represent any other words except I am Groot. So overall, there are 4 words in the dictionary. So we will assign integers for each word. And it not necessarily start with 0, but it's a common pretext that we indicate each word from 0. So this is actually a pretty simple and nothing fancy here. It's just using one numbers to present the word. Actually, the idea of the dictionary lookup exists long before the creation of computers. This is the famous Morse code. We use the dashes and the dots to represent the letters and the numbers. Basically, it's the same thing, right? We just use in dictionary lookup, we use our integers to represent each word. Here, we use dash and dots to represent the letters. And I call this, there is a reason that I call this stage as prehistory, because there are so many problems of these representations. The first one is when we assign an integer to each word, we accidentally impose some unnecessary ordering assumptions. For example, we know that 1 is greater than 0. Does that mean the word M is greater than I? It's meaningless to compare different words, but as far as the computer sees, there are an ordering of these words because we represent each word using the integers. The second problem is the integers do not contain any information. Basically, we are using one symbol to print another symbol. It's nothing progress here actually. Integers are still symbols, so it's just because we use integers because computers are good at numbers. So that's the only advantage for this representation. And the last problem is the dictionary can grow to infinity. As I mentioned earlier, that we are creating new words every day, and the language is changing every day. If we track every word we encounter, the dictionary can easily grow to infinity, and it is meaningless to track every word, right? Okay, when living in the prehistory, we will enter the age of the Middle Age, in which we will use one-hot repetitions to present each word. So in the first part of this lecture, I have talked about the one-hot repetitions, and I will rephrase it here. It's basically the vectors. Basically, we will recognize the previous integers, and each vector is high dimensional, and the size of each vector is equal to the size of a dictionary, and each dimension is represent one word. And this repetition is quite simple, but actually it is very useful in practice. That's why I called it the Middle Age, because we have been using it for many years. One advantage is it eliminates the wrong ordering assumptions. So we cannot directly compute the vectors. We cannot say one vector is greater than another vector. So it's one advantage that there are no ordering assumptions about the words. But the other problems that remain. First, it carries no semantic information. Basically, we just change from integers from the dimensions. So this still cannot carry any semantic information. And the second is also the dimensions can be infinity. It's really a problem, because the size of a dictionary can be in millions. So if we maintain a vector that has millions dimensions, and there are so many vectors in the memory, it's a disaster for computers to handle these things. Okay, the next stage is the enlightenment stage. In this stage, the concept of word vectors were proposed. So in this stage, instead of using one-hot representations, using extremely large dimensions vectors, we use a dense low dimensions to represent each word. For example, originally, the word boy is represented by a large dimension vector, but it's a binary vectors. Everything else is 0, and only the dimension presenting word is non-zero. And in word vectors, we will present the word of boy to be a fixed dimensioned real number vectors. So basically, it can be geometry speaking, the word of boy can be anywhere in the vector space, just not in some axis here. So it has a bit by doing this change, it has the ability to contain semantic meanings. Because now it can be anywhere in the vector space. So we can say that that region is represents concept of color, and the other region represents concept of sequence. So it is possible have the it makes it possible to let the vector space contain some semantic meanings. So so the question is, how do we get this vector space? So the earliest paper I can find about using neural networks to generate word embeddings is this paper called a neural probabilistic language model. It was published in 2003 by the Banjo. By the way, Banjo is he won the Turing Awards in 2018, which is the highest honor in the field of machine learning. Possibly, I think it's the highest honor in computer science. So basically, this paper describes how to use neural network to train a language model to generate word embeddings. But at that time, this model is limited by the computing resources, and limited by the efficient algorithm. So although we already have the concept of word vectors, and we already know how to generate it, but in practice, we still cannot have a high quality word embeddings. So that's why this stage is called enlightenment. We have a very good idea, but we do not have the resources to implement it. And the advantage of the word vectors is, first, it's clearly it's an ordering information, so it can be placed in the space everywhere. And it has ability to carry semantic informations. And also it has fixed dimensions. The fixed dimensions is actually very important because it makes life so easy for us to handle these vectors. Especially nowadays we have GPUs, so fixed dimensions is high dimension vectors is no longer an issue for us as long as they are fixed. So, but the disadvantage of the word vectors this time is it is too expensive to train such a vector space. It requires a large amount of text data, and we do not have the efficient algorithm to train the model. Okay, then we will enter the industry age. In this age, we have enough resources, and we have efficient algorithm to produce the word vectors we want to. So in 2013, a team at Google led by Thomas Mikloff, they published a word embedding template called Word2Vec. In this paper, they proposed a few techniques that can help us speed up the training process of a neural network to produce word embeddings. I personally think this the creation of Word2Vec really reshaped the whole community because using Word2Vec, we can generate high quality word embeddings, and these embeddings can be fed to other NLP tasks. So at that time, at about 2014, 2015, among these years, researchers just replaced all the original word representation with this new word embeddings, and it improves the performance of many NLP tasks. So this shows that the repetitions are really important. So if we have a good repetitions, it will be very easy for us to build a high level NLP tasks. So this famous equations, King minus mine plus woman equals queen, comes from the Word2Vec paper. So, but although I've said a lot of good things about the Word2Vec, but it cannot handle everything. It cannot resolve every problem of the language. There are still some limitations of Word2Vec. The first one is it still needs a fixed dictionary. If we want to add more words to a dictionary, we have to retrain the whole model, which still is very time consuming. And another way is it cannot handle the phonology and the homonymy problems in language. It is problematic if one word have multiple meanings and we map that word to one single vectors. It doesn't make sense because the word can mean different things. Why should we use only one vector to represent the meaning of that word? And the next problem is the out of vocabulary problem. For example, if we want to map some word not in the dictionary to the vectors, what do we do? Actually, we cannot. If that word is not in the dictionary, we do not know how to map it into the vector space. That's the limitations of the Word2Vec. So in this industry age, there was another famous model called fast text, which was published by Facebook AI Research Lab in 2017. The fast text is quite similar to the Word2Vec, but it overcomes the OOV problems. Actually, I think that they overcome this problem in a very clever way. So in fast text, instead of map each word to a vector, fast text will first decompose each word into subwords. For example, here the word where will be decomposed into WH, WHE, HER, ERE, and RE, the 5 different subwords. And the model will learn repetitions, vectors for each of these subwords. So when we need to generate the embeddings for the word where, we will apply a linear transformation upon all the vectors of these subwords. So it's somehow it's a dynamic generate the embeddings. So when we have a word that's not in the vocabulary, that word will be first decomposed into subwords that already in the dictionary, and we will apply the same linear combination, linear transformation to generate the embeddings for the unknown word. It's quite clever. I think it's a beautiful way. It's an elegant way to resolve these OOV problems. Any questions about word2vec and fast text? Okay, so next we will enter our modern age, which is we improve the quality of word embeddings by making a difference between the type vector and token vector. So the type vector means the word. It means the word is context independent, which means the same word in different sentence has the same representation. The representation only depends on the word itself, and everything else, everything we talked about before from the prehistory and the Middle Age and the Enlightenment and the Industry Age, everything else, everything that representations can be classified as type vectors. But now, in modern age, a new concept of token vector was proposed. Token vector means that the vectors is context dependent. So what it means is the same word in different sentences have different representations. Let me use examples to explain this. So here we have two sentences. The first one says that I need to deposit some money to the bank. And the second sentence says that I'm walking along the river bank. So there are the word bank appears in the two sentences, and it means completely different things. So in type vector, like the word2vec and the fast text, we will assign the exactly same vectors for the first bank and the second bank. So because these word vectors only depends on the word itself, but actually it makes no sense because in the two different sentences, the bank means different things. So that's why we propose the concept of token vectors. The token vectors will assign different vectors for the first bank and the second bank. So the vectors is determined by the word and its context. So it's a quite improvement because the word embeddings can contain more context information for that word. So if the creation of type vector marks the age of industry, then I think the creation of BERT marks the modern age. BERT model was published in 2019. Google published this important paper in word presentations. So although this paper was not the first paper that proposed the concept of token vector, but it is the paper that really reshaped the representation again, because these representations contains much more semantic meanings than the word2vec, and it improves the NLP tasks again in many tasks. So okay, at last I want to give a little summary of the different stages of our history of word representations. At first, we are in the prehistory age. At that time, we only use integers to represent each word. There are nothing fancy. There are nothing beautiful here. It's just a dictionary lookup. So then we try to vectorize these integers into one-hot representations. That's where we enter the Middle Age. And although the one-hot representation has many problems, but it is practically useful in most cases, and we have been using the one-hot representations for many years. Then we will enter the Enlightenment, which the concept of dense vector was proposed. But at that time, the concept of dense vector only exists in theory because we do not have enough resources to train the model to get these vectors. Then we will enter the industry age. we have the ability to train the neural network to generate the high quality word embeddings. There are two famous models here. One is word to vec, another one is called fast text. Don't be confused. Yes, there are so many other models that were proposed in the age of industry. I only point out use word to vec and fast text as examples. And next, we will enter the modern age by distinguish the difference between token vector and the type vector. So of course, there are also so many other models except the BERT, but I think BERT is the first one that really matters. So, so what's the next? Actually, I don't know. The research progress is usually surprise you in a different way. So, but I'm ready to learn something new for the next stage of the word representations. So here is the takeaways. The first one is the simple idea is not simple before it is proposed. So it seems nature to think that now it seems to nature to think that we should use type token vectors instead of type vector, or we should use dense vectors instead of one-hot representations. But it's not so easy before the creation of this concept. So when you in the industry of in the age of prehistory or in the history of Middle Age, it's not easy for you to come out with new ideas to reshape the whole world. So so another takeaways here is the research is always built upon the previous work. As we can see here, we start with prehistory using integers and we vectorize into extreme large one-hot representations, and then we go to the dense vectors, and then the dense vector evolve into token vectors. So this we can say continuities here that the research is built on the previous work. It will always based on the other one's work. And at last, the computers and the humans see the world differently. Human brains are actually very amazing things. It is designed to be very good at handle the symbols. We can read the text very easily and understand their meanings. But for computers they compute different things. They are good at numbers. They are good at memorize, but they make the ability to do the reason. So if we want the computers to understand the language, we need to put ourselves in the view of a computer. We need to represent the language in a way that computers can understand. So I think that's the problem of the word representations, and also that's really interesting research directions to build high quality representations for computers. So this is the end of this talk. So ask me anything if you have any questions.
Yichu, thank you very much for your talk. Any questions? Please feel free to unmute yourself or type in the question. So, okay, there's one question on the chat. How does this work for character-based language like Chinese?
Okay, this is an interesting question. It's based on the tokenizer. How do we create the dictionary? So basically, in Chinese, we will break the words into I don't know how to say that. The letters. I think that each single word, the character, right? It's a character. So we will put every character into the dictionary, and we'll have vector mapping to these characters. So when we creating the embeddings for a word, we will put these character vectors through the neural network to produce embeddings for that word. Okay, does that answer your question? So basically, it's just like English. For English, we map a word to a vector, but in Chinese, we will map each character to a vector. But it's not that simple because when we generate the words, the embedding for the Chinese words, we will go through a network to dynamically generate embeddings based on context.
So in other words, if you have, say, if you have an English sentence, each word in the sentence gets an embedding, right? So
Yeah.
the same thing is that if I have a Chinese sentence,
each
character, which is a word, is going to get its own embedding.
Yeah.
But the other question is, there's also a weird thing about, say, Chinese characters, because Chinese character itself can be decomposed into different parts, and some parts itself also has meaning.
Yeah. Yeah.
So I'm curious as whether people have also thought about
That's a very good question. I know there are a few research work. They're trying to decompose each character into different parts. Yeah, and they will assign the embeddings for that part. And because these parts also contain some information, so it is reasonable to think that if we break down to these parts, it can be have more can generate more more high quality embeddings. Yes, that's also a research directions, and I have seen some work on that.
Cool. All right. Any other question from the audience? Okay, so if there's no more questions, thank you, Yu for giving us a guest lecture to go a little bit deeper into natural language processing. Just a reminder for everybody, homework, there's a homework due tomorrow with 2-day extension with penalty. So thank you very much, and have a good rest of the week.
Thank you.
Thank you very much.